These are the notes for LT4 in the thermodynamics unit, and the target says, I can apply thermal expansion to engineering designs such as bimetallic strips and the bridge construction and bridge construction. Alright, and we'll apply it to more than that, but those are a couple examples. Here in class, we discuss this question. So why does the density of most substances decrease as their temperature increases? Because that's an important part of thermal expansion. And what we eventually get to, what we think about here is, well, what is density? All right, and that's kind of a throwback to middle school. And the density of a substance is its mass divided by its volume. Okay, you may have learned it. It's kind of a goofy thing, but if this is a heart and you break it, very sad. All right, that's how you can remember the two little humps on the heart are the mass, and then the tip of the heart is the volume. So mass divided by volume. So when things are heated, their mass shouldn't change, because that's just how much stuff something contains. But we know their volume does change, because remember those IPFs from kinetic theory? Those interparticle forces go down. So there's less holding the substance together, which means the volume is going to go up. So I'm just going to pick a random number. Let's say we had a mass at 10 kilograms, and this volume starts at 1 cubic meter. Well, the density is 10. But what if we doubled it? All right, what if the volume expands so it's 2 cubic meters? Well, now we have a density of 5. So as things warm up, at least most things, their interparticle forces weaken, they get farther apart, and then their density ends up decreasing due to this formula. All right. So we're going to start right out with a definition, and our definition is thermal expansion. And it is kind of exactly what it says in the name. It's what happens when the volume of a substance increases due to an increased motion of molecules. Increased motion of the molecules. So whatever is making it up, they jiggle faster, and we saw that on the PhET simulation a while back, where as you go from a solid to a liquid to a gas, you can see those molecules jiggling back and forth faster and faster and faster, and that's what ends up weakening those interparticle forces. Just so we have this in our notes, remember density is this mass divided by volume idea, and so if we make this bigger, okay, if that volume expands, then our density goes down because we're dividing by a larger number. I would encourage you, if you're listening to these notes because you were not in class, to go to Moodle, watch the LT4 video on thermal expansion. It does a great job of applying this and showing you kind of in a drawing, an animated drawing of what's happening here. Because what we're going to do is just apply this to a lot of things. And so it's going to feel a little random, but let's talk dental fillings. I know I'm blessed with a few. But if you think about whatever the dentist is going to use in your teeth, so they give you those shots that feel like awfulness, and then they put the goop in there and they harden it. Okay, it's an alloy type of goop. But I'm assuming it took them a while to figure out what to make that out of. And one of the factors they had to determine was, well, you're going to eat things that are hot and cold, right? And so if you eat something hot, so if you eat some soup, your teeth actually expand a bit. And if you eat ice cream, your teeth are actually going to contract a little bit. Okay, they get cold. Well, you want these dental fillings to have the same rate of expansion as your teeth. Because imagine if you're eating your soup and these dental fillings were to expand faster than your teeth. Okay, they would essentially bust your tooth apart. So imagine how miserable that would be. So hopefully there weren't too many unfortunate people early on that had to learn this the hard way. Hopefully they figured that out in a lab. So there's just one example of how we would apply thermal expansion to something kind of in the medical realm. In the video, they show you railroad expansion joints, but also think bridge expansion joints. And most of us have been across the Mackinac Bridge, so It's kind of that middle lane there, where if you go over it, I think it's green, and it makes a noise, and you guys probably haven't driven over it yet, but it kind of pulls the car back and forth. And what those are built in there for is a couple things. One is for wind. When we get into the wave unit, you'll learn that we don't want resonance to occur within the bridge. But the other one is they're made out of metals. And metals have huge rates of thermal expansion. So you might think at first, man, we don't want them to expand. But think about what a metal can do. Metals can expand and contract without breaking. Okay, think about spring in Michigan when you've got potholes all over the road. All right, because in the winter, those roads get really cold and that pavement contracts, and then here comes sunshine in the spring, and they expand. And that over time, the pavement can't take it, the concrete, and it kind of busts apart. I don't know about you, but I don't want a bridge to bust apart. And so if you go across that bridge in January, I mean, you could be 0 degrees. It could be freezing up there. And then you go across in July, it could be 100 degrees. That's hard. Okay, that's tough for a bridge to take. And so by putting these metal expansion joints in there, it gives it some give. So it can expand, it can contract, and it doesn't break. All right, that's a big deal. With the railroad joints, then what you saw is that we don't get breaking, but we also don't get any buckling of the railroad tracks. So you see how they put some space in there. You don't want those tracks when they expand to kind of turn upwards. That's going to derail a train. Similarly, you don't want them to pull apart if they contract. Okay, so these joints are kind of put in there to give them a little bit of flexibility, a little bit of room to grow and room to shrink. Last thing we're going to talk about are what are called bimetallic switches. So think about the word bi. Bi infers two. Therefore, there's two types of metals. And what's unique is each metal has its own expansion rate. So each metal has its own expansion rate. Now, I would encourage you to go into Google on your Chromebook and type in bimetallic switch, because it's going to be way better than the one I'm drawing here. But let's say that that's material A and that's material B. What will happen is if you put this in a device that turns on and off due to temperature, so think like a furnace or a refrigerator, something like that, where for like your furnace in your house, if your house gets too cold, it turns on, and it runs until your house warms up to whatever level you have it set at, and then it turns off. What happens is within these devices, there's these two metals that are soldered together. Okay, it's just like a type of metal glue, if you want to think of it that way. And so, I tried to figure this out. You know it's going to be ugly here, but something like this. All right. And so here's our two metals. We'll keep it the same, where that's A, that's B, and then B, A. I'll just do the squigglies to show you it's two types of metals. So here's your house warming up, right? Here's where it's neutral. It's just kind of in between temperature. All of a sudden your house starts to, we could say it warms up, and it looks to me like B is not able to expand as fast as A. So A is expanding crazy fast, and it causes it to essentially bend around B. All right, so it looks like in this situation, A has a higher expansion rate. But then here, okay, as we cool down, B starts to shrink in, which bends A back around it. All right, so when it warms, A expands up this way, and then as it cools, B kind of shrinks in to buckle it the other way. All right, so that's just a way that switches work. And it wouldn't just be a furnace, like I said. It could be a refrigerator, anything that responds to to energy changes. So think about an oven when it's preheating, a toaster to pop your toast up, whatever. All right, so that's the idea of thermal expansion. And again, I encourage you to do some Googling, look at some pictures, and to watch that LT4 video on Moodle. Good luck.